All right, hello everyone. Welcome to my channel. I'm Thomas, and this is a channel for educational videos. Today is video 121 on the reciprocal system of theory. The reciprocal system of theory is a theory of everything that was first proposed by Dewey B. Larson back in the 20th century. He died back in 1990, but his work has been carried forward by others, especially Dr. Bruce Perret, who died back in 2020, and Drs. KVK Nehru, Dr. Gopi Krishna, and others. And the basic idea behind the reciprocal system is that we have a universe of motion. The universe is not made out of matter. The universe is not made out of energy, but it is made out of motion. And matter and energy are actually just specific kinds of motion, as are every other scientific phenomenon that we know of, including acceleration and pressure and magnetic flux and capacitance and impulse and force and speed and energy. We said that already. There are others, but really any combination of space and time, because for Larson, he distinguished his theory because other people have come up with this idea of a universe of motion, but he distinguished his theory from everybody else's by defining motion as the relationship between space and time. And so all of these different kinds of motions are just relationships between space and time. Now, space and time, so a relationship generally implies a fraction, a ratio. And time and space are both multidimensional. Now, when you have a fraction, you have a reciprocal relationship, like 2/3 and 3/2. If you invert them, then you have the reciprocal, and that multiplies out to being 1. And so what adheres to one time or space also adheres to the other. They both have the same qualities. And space we know to be 3 or more dimensions. Therefore, time is 3 or more dimensions. Larson calls that coordinate space and coordinate time. And time is always flowing and progressing, getting later and later. And so therefore, space is also flowing and progressing, always getting farther and farther apart. Evidence for this is the Hubble telescope's observation of the recession of the distant galaxies. And Larson calls that clock time and clock space. So everything, all these different scientific qualities are just relationships between space and time. So for example, speed is space over time. Energy is time over space. So you can also understand that speed and energy are reciprocals of each other. Matter is actually timed to the 3rd power over space to the 3rd power. And we will get into what that really means at a certain point here. But the other aspect of space and time that is relevant is that they both come in discrete units only. They don't come continuous, they are in chunks. And so you have a minimum unit of time and a minimum unit of space, 1 unit. And 1 unit of space in 1 unit of time is the speed of light. So the speed of light is not the maximum speed of the universe, as Einstein would claim. In Larson's universe, the speed of light is the midpoint or the null point or the neutral point of the universe, which makes sense because if you have a universe of motion, then motion is really the common denominator of everything. Um, and you really don't have anything that's not in motion. So even when you are when you are perceiving no motion, you have this background motion of the speed of light in all directions. Larson calls that the progression of the natural reference system. So this calls him to really have a conventional reference system, which is, what we recognize to be stillness, and taking the measurements from that point of stillness. And then you have the natural reference system, which acknowledges that everything is moving outward at the speed of light in all directions. And so that is the datum from which you take your measurements. You take your measurements from the speed of light, not from zero. And so that creates a lot of different dynamics. Okay, now we are right now looking at going through the transcript of one of his interviews, or really one of his few interviews that he did back in 1984, when he was an 85 or 86-year-old man, 6 years before he died. And he's being interviewed by this guy named Jan Sommer. And he's going over various things. Right now he's talking about the periodic table and how he kind of came up with his idea about a different periodic table, and how he recognized that there were really three variables going into the properties of matter, and one of them is represented by the horizontal rows of the periodic table, and one of them is represented by the vertical rows, but he has this other one as well. So he's talking about that. So we're going to take over right at this point. So here's Larson. So in that way, the solid is a simpler structure. In the other direction, the value of tackling more complicated substances first is that then you have series relations. The series beginning with sodium, for instance, is quite well defined. So I began with the sodium-potassium series, and I took that as a two-component system, as the chemists do. But before I got done, I realized that I had to introduce a third number. I got some results with the third number that I couldn't get with the two. But the minute you get into three numbers in anything like this, your immediate reaction is, those must be dimensions. That's an obvious conclusion in a three-dimensional universe. So that was the thing that led into that. Question. And then from that, you deduced the atomic structure? Larson. Yes. When you got dimensions, then the next step was to identify the numbers numbers with the rotations and the speeds. Of course, there were a lot of different angles to work out on that, because even though the structure may not be too complicated, in certain ways it is complicated in that there are alternate ways of fitting into the reference system. We still have more work to do to clarify this point in the theory. Question. You mean the coupling to the reference system? Larson. That's part of it, yes. Question. So you had these three dimensions, and you were working also with the photon. You realized that simple harmonic motion could be permanent. Then somehow you brought these two ideas together and concluded that the photon was actually one of the building blocks of the atom. Larson. Let's put it this way. The idea of the photon as simple harmonic motion was really the same thing that Galileo had in respect to translational motion. According to the previous ideas based on Aristotle's work, it was necessary to have something to cause continual motion. And the problem was to identify what it was that caused the proton to continue. The photon to continue. Actually, I've read that completely wrong. Let's go back. Aristotle's work, the previous ideas based on Aristotle's work was it was necessary to have something to cause continual motion. And the problem was to identify what it was that caused the motion to continue. I think that Aristotle himself used angels to push the planets around. Well, Galileo discovered the fact that you don't have to have anything to explain that. That is, motion, because it's motion, is continuous. Now, I was merely extending the same thing to this simple harmonic motion, because once started, it is nothing but a motion that continuously changes direction, and consequently, it requires no more explanation than translation. Now, once you have a vibrational motion, you have an object in space. For the purpose of explaining radiation, all I had to do was to let this object move in a direction perpendicular to the vibration. There were other questions in connection with radiation, of course, that I still hadn't clarified, but up to this point, that was all I needed. You can't rotate until you have something that is going to rotate. So that, to me, we were talking about this yesterday, but that to me gives evidence that Larson didn't really understand the primacy of rotation. You can have translation without something to translate. You can, I don't know. Maybe I'm not understanding what he's saying correctly there. You can't rotate until you have something that is going to rotate. So that's really how he's saying that the atom is being formed. First, you have to have something, and then you rotate it in two different dimensions, and possibly a third, and that is what creates the matter. But you can't rotate until you have something to rotate. And Larson's followers, his revisers, disagreed with that. And they really even said that the photon itself is the result of a birotation, of a counter rotation, and that the simple harmonic motion is merely the residue of the interference of those two rotational motions. And that the rotational motion is just as primary as the translational motion, and so it doesn't require anything that you need. You don't need any angel to push it around to make it happen, the way that Aristotle was saying about planetary motion. And even though planetary motion, in both of their schemes is rotational, he doesn't seem to be applying it here. So this is an interesting point, and it's a point that has been a sticking point in the reciprocal system for many, many years, since Larson died. And since Bruce Perret and KVK Nehru started, to kind of look toward the birotation as the source of the photon. So, the photon is your simple harmonic motion, your sine wave. And that is, for Larson, that's a combination of a translational motion and a vibrational motion. So you've got, when you combine both of them, you get a sine wave. But you also get a sine wave when you have two counter-rotating motions and you interfere them. A sine wave comes out of that too. So those are two different ways to look at the photon, and they create very, very different results. Okay, back to the questioner. So basically, you took the simplest object you could conceive of, Larson, I'm developing from the standpoint of simply a relationship between space and time. And that's the first thing I was able to derive from that. So that's all I needed. When I got something that would work, that is the most likely thing anyway. So that was the thing then that I decided to rotate. So for his atom, he's got the vibration, he's got the simple harmonic motion, and then he rotates that in a perpendicular direction and rotates that in a perpendicular direction, and that is what creates matter. So you really got three components there, and that makes sense because matter is in Larson's denominations of time and space, matter is time to the third power over space to the third power. Well, we know that space to the third power is just volume, XYZ coordinates. It's this far in this direction, this far in this direction, and this far in this direction. So that's volume. So you have 3 dimensions of time in a volume. That's matter. And so the first dimension is the photon. The second dimension is the rotation. And the third dimension is the other rotation. And that also kind of sheds some light on actually what time is. When you think of space, you think of it as in a direction, not a vector, but just an expanse. From here to here, how much space is that? Or from here to here, how much space is that? But with time, you're not so much dealing with a translational motion. You're dealing with rotation. Just like a clock. A clock is, measured by how much rotation you have, how much angle you have, and the days of the week or whatever. Monday and then Tuesday, the difference between that is a rotation of the Earth. And so time is really a rotational thing, whereas space is really a translational thing in this sector of the universe. Now, if you were moving faster than the speed of light in what is called the cosmic sector of the universe, then I believe it would be inverted, and time would be the straight one, and space would be rotating. So, okay. This is what you can get into with the reciprocal system. Once you understand the rules, then you can start to, do the induction and the deduction that Larson used to create his system. If this, then that. If this, then that. Well, if this is what happens, then this is necessarily going to happen. And you can learn to understand Larson's process of deduction. I did about 15 videos on that earlier. That is his coming from his talk that he gave. I don't remember the date that he was giving that talk, but it was. It's called The Outline of the Deductive Development of the Reciprocal System. If you look back about 3 or 4 months back in my videos, you can watch those 15 videos that I did on going over his deductive development of the reciprocal system. And then you can see how he developed it, and then you can learn to develop your own system and, see how it agrees with his system. Okay, back to Larson. I'm developing from the standpoint of simply the relationship between space and time. That's the first thing I was able to derive from that. So that's all I needed. When I got something that would work, that would is the most likely thing anyway. So that was the thing I decided to rotate. Then the next problem was to see how that fitted with the figures that I had, the results of observation and measurement. And of course, that took a long time. But the thing that kept me at it was that there was continuous progress. You could see the thing developing in a natural and easy enough manner so that it was clear that you were on the right track. When I say easy manner, I don't mean that I saw it easily. It's something I should have seen. I've had that experience so many times. I would come to something as a result of a long and difficult period of work and then recognize that it was something that if I had been smart enough, I should have seen it immediately. Question. You mentioned once that at the beginning you went into a lot of blind alleys, but I imagine that after you got these results, you were making pretty steady progress. Well, the blind alleys were primarily in the inductive phase of the work. You see, there were really two phases to this operation. There was an inductive phase in which I was doing, as you always have to do in inductive reasoning, you start from the observed and measured facts and work back up toward the general principles that govern those. That was what I did until I arrived at this concept of the universe of motion and described it in the postulates. That was back around 1950. So the work up to 1950, the inductive phase of it, was the hard work. Since then, it has been the deductive phase. I have simply gone from these postulates and worked down toward the consequences. In the original development, starting in about 1950 and into the deductive part of it, I was working mainly with these general principles. But since I had gone up along a certain route, when I started down, I had this information pretty well in hand in these particular fields, such as interatomic distances and the liquid state. Those were the things I used to get up to the general principles, the postulates. Coming back down again in the deductive phase was easier because I had already covered them in the other direction. I never had so much trouble with blind alleys after I started on the downhill proposition. In the deductive phase, you don't get into blind alleys so much. The problem there is usually a case of not seeing where to go next after reaching a certain point. But if you see it all, you usually see the right direction. That was not true in the inductive phase. It's something like the difference between the two kinds of calculus. In the differential calculus, you always get an answer. You follow the rules and you go directly from the problem to the answer. Well, that's not true in integral calculus. You don't know whether the answer is there or not. That's the same kind of thing in inductive and deductive research. In the deductive research, if your theory is right, it's just a matter of finding the right avenue of approach and seeing it out, setting it out. But in the inductive phase, you don't know whether you've got an answer at the end of the road or not. And you have nothing to tell you if you're on the right road or not, unless you get into trouble. Now, when you do get into trouble, you're not sure whether it is because you're not smart enough or because you're on the wrong road. For instance, I spent, I would say, at least a couple of years on a trigonometric solution to the question of the elements. But because I was figuring that maybe it has something to do with the position of the elements in the solid state. I even got some interesting results from that. But finally, I was forced to conclude that it didn't work. So I discarded that, threw out 2 years of work, and started back again on a different basis. Okay, now to me, that quote there, that answer to that question is pretty much gold. And that is really deserves to be gone over and over again, because he's explaining, the inductive phase is uphill, the deductive phase is downhill. In the same way, integral calculus is uphill and differential calculus is downhill. And that's how you get to solve problems. Okay, we will resume at another time tomorrow in this interview. And you have a great day. Thanks for tuning in. Hope to see you soon.